Alright, hi, welcome to the video on logic gates. I'm going to be showing you each of the basic functions, what they do, truth tables and schematic symbols and stuff like that, and a little bit about the importance of logic gates and how they're used. So first off, before I get into this, logic gates themselves, in case you don't know, let me draw a little box here. Alright, so what are logic gates? Essentially all logic gate is a Boolean function. It's just like you have y equals x squared when you start, we're in school. It's just a function that you have inputs and you have one output, and inside you have the function itself. And since these are Boolean functions or digital functions, they only deal with ones and zeros. So we have any number of inputs depending on the gate itself. And we have those inputs, they come in there, the signal is processed, and we get an output, which is going to be true or false, high or low, 1 or 0, whatever you want to call it, and that's basically it. With these logic gates, with these functions, they're the basis of computing. We can take these basic functions and we can cascade them and build basically whatever you can imagine. And it's kind of hard to see that in the beginning, but as you go on, you can kind of see how important they are. They're so simple, but it's important to understand them, and not as important right now to understand exactly how they're implemented in a big picture sense, but just kind of understanding what they do. So they're just digital processing functions. The signals go in, they're processed, and you get your output. Logic gates, these original functions have been around forever. By forever I mean over 100 years, before we had the transistor, before we had any of that stuff. Originally these were actually done with gears. They called it the analytical machine. It was the very first computer before we had computers. Then we went to relays, it went to vacuum tubes, and eventually the transistor came out and allowed them to be scaled, and allowed us to get to make computers the way we see them today. So inside these gates, let's draw, let me draw an AND gate real quick. Hopefully you guys can see that. Let me erase this guy. So inside these gates themselves, they're implemented with different ways. Right now, like I said, transistors. Inside any of these gates, you'll have a number of transistors in a certain way to make the function work. Anywhere from 2 up to 10, 15 transistors in each one. The NOT gate itself is built with 2 of them right now. We can use these to build whatever we want. So that's that. Let me go through all these and show you the truth tables for them and the schematic symbols and whatnot, and how each function works. And then from there, we can go from there. Okay, so let's start with the NOT gate. It's the most basic one. It's used everywhere. It's important. It's also known as an inverter. Why? Because that's what it does. Okay, the symbol is this. We have the input. It's a triangle with a bubble on the end, and we have our output. An inverter will always have one input and one output. Okay, I'm going to call the input X and the output Z. Why? Because I can. Okay, so how this works is you have an input. It's either going to be a 1 or a 0. Because we're dealing with Boolean or digital circuits here. So you have a 1 or a 0. The voltage is either high or low. Low means 0, high means 1 in this case. So if it's a 1 here, the output is a 0. If it's a 0 here, the output is a 1. It's a NOT gate. It's an inverter. It simply just inverts the signal. And the truth table, well, it doesn't get any simpler than this. This is the input, this is the output. Never seen a truth table before. All it does is take all the possible input combinations. If we had three inputs, then we would have a total of 8 possible combinations. It's 2 to the number of inputs. That's how many combinations you have. If we had 2 to the 2 is 4. We'd have 4 combinations. If we had 8, 2 to the 8 is whatever it is, we'd have that many combinations. So that's all that is. Since we have one input, we just have 2 possibilities, 0 or 1, and the output is going to be the opposite of the input. So that's all that happens is, if this is a 1 and it goes to 0, it goes in, whatever the propagation delay is in there, it processes it, and then the output reflects that, and that's that. So that's the NOT. Let me move on to the AND and the NAND gates. These little erasers are so handy. All right, so that's good. I'm gonna group the last here because these are kind of work together. So we'll do the AND and NAND together. Let's start off with the AND here. Let's see, make sure you guys can see that. And I like to write it in all caps. Just remember, it helps you remember that it's and not the word and. So this is AND. The symbol, I'm going to draw a 2 input AND. So it looks like a big giant bullet. I don't know if you remember, you ever played Super Mario and that big bullet would come across the screen, and you'd either have to duck under it and jump on it and kill it. That's basically the symbol. This is 2 inputs, so I'm going to do that. I'm going to label them X and Y, and then we'll label the output Z again for clarity. NAND, draw that too. So NAND, not AND. This essentially will be the opposite of the AND gate, and you'll see it's the same for the OR NOR and the XOR and the XNOR. They're just opposites. So AND gate, let's do the truth table. So like I said before, we have 2 inputs. That means 2 to the second is 4. We're going to have 4 possibilities, and we need to look at the inputs and outputs for each one. So the 4 possibilities are these. Okay, and how this function works. It's only true. The output is only true when both of the inputs are true. So when we have, it's only a 1 here when we have 1s on both of the inputs. Okay, and that's where the term AND comes from, because they all have to be true. And X and Y have to be true. Otherwise, if they're not all true, then we get a 0 on the output. So it's that simple. Just look at it. If this had more inputs, you know, if we had 50 inputs on here, they would all have to be true for the output to be true. If any one of those is not true, the output becomes not true. So for the NAND gate, exact same symbol, except for it's not AND, so we have to put that little bubble on there. So what happens here, X, Y, is our output. One of the drawbacks to being left-handed is that it's hard to write on these things and not smear it. Okay, so the not AND, what happens here is you have the inputs, the same signal is processed, and then that little bubble means inversion. So what happens is the not AND gate or the NAND gate ends up being the opposite of the AND gate. So here we had, it was only true when they were both true. Here, it's only false when they're both true. So what happens is, it's the exact same thing, and then it's inverted. So it's true all the time except for when they're both true, and then it becomes false or goes low. When I say false and 0, by the way, that's not necessarily true, because you know there's different. We could define the one to be. We could define the high voltage to be false and the low voltage to be true. But for now, just remember that X and Y, we have a 1. It's only going to be a 1 here unless they're both true, and then it becomes a 0. It's the opposite of the AND. Hopefully that wasn't too confusing, but it's a simple thing, so I'm not too worried about it. Okay, 2 more groups to go through real quick. OR, let's see, we did these 2. OR and NOR. You guessed it, or, not or. Alright, let me erase these truth tables. Okay, the symbol for the OR gate, like the AND gate, except for this part here, ends up being curved. So we draw it like that. And the NOR, not OR, same thing, inversion bubble. Okay, OR gate. You could probably guess it by looking at it, but the truth table ends up being pretty simple. The OR gate, the function works if X and Y, if either one is true, either OR is true, then we get the output to be true. So in this case, these are both not true, so we get a 0 here. One of them is true, good. One of them is true, good. They're both true, that's fine. As long as one of them is true, the output will be true. So if we had 100 inputs, as long as one of them is true, we're good. Nor, not or, complete opposite because of the inversion, and we can just look at it like that. If you can just remember one of them, you can remember the other one's going to be opposite, right? So the not or, it's true when all of them are not true. It is false, the output I'm talking about, when any one of them is true. Okay, that's simple. That's the gate. Hopefully you can read it. It's a little sloppy, but that's okay. Okay, last set, which I think is a cool set because they do cool things. Okay, so last set is going to be the exclusive or and the exclusive nor. Hopefully you guys can see the truth tables on there. Okay, XOR. This schematic symbol, using two inputs again, we could, actually that's how the XOR works, is we just have this extra little dot here, or little line here, sorry. And the XNOR, same thing, except for it's the exclusive NOR, so it's the, we need the inversion bubble on there. Okay, how does the truth table work? Okay, this is cool. In the OR gate, remember, we had to have either one of them true. In the exclusive OR gate, it's only if one of the two is true. So here, neither. One of them is true. One of them is true. They're both true. So this one ends up being false. Because with the regular OR, this would be true because it's only one or the other. Exclusive OR, it's only when one true and when one's true and the other's not true. So this ends up being like that. The exclusive NOR ends up being just the opposite, just like the other ones. It's inverted. So this one's true when they're both not true or both true. This one's the opposite way around. Real quick, this is kind of cool. The exclusive OR function, essentially what you're doing is checking to see if both bits are the same. The exclusive function, same thing with the NOR. These are both not true and these are both true. So we have a 0 here. These are not the same, right? So we have a 1 here. So what are we doing? We can look at this. We can look at the output and see if it's true or not with either one of these. And we can say, oh, well, those two bits are the same or those two bits are not the same. So this ends up being a comparator. And with comparators, we can do all kinds of cool stuff. You can build adders and multipliers and all kinds of stuff with them. Very powerful function. But again, that's later on down the line when you actually start building circuits out of these. And yeah, so those are the functions. Those are how they work. If you have any questions or if I confused you, feel free to chew me out or send me a little email. That's fine. I'm happy to answer anything. Put it in the comments or whatever. That's fine. There's other videos if you want to know. I would suggest going in and doing Boolean algebra and stuff. I have some videos on that to help you, and that's basically it. So hopefully that helps you out, and yeah, hopefully not too confused.